Hello and welcome to today's lesson on refraction, which is found in the waves topic of GCSE Separate Science Physics. So in today's lesson we're going to look to understand the laws of refraction by looking at the refraction required practical, which if we're successful and we learn in today's lesson means we'll be able to detail the process of refraction, understand that refraction is due to the difference in velocity of the waves in different substances, and we construct ray diagrams and wavefront diagrams to illustrate the refraction of a wave at the boundary between two different media, which falls into the following part of the GCSE Separate Science Physics specification 4.6.1.3, reflection of waves and including refraction, which is only part of the physics topic or the separate science course. So all waves can carry out three different processes when they hit a material. Reflection, where a wave hits a surface and bounces back. Refraction, where a wave goes through a surface and changes speed and direction. Or absorption, where the wave's energy is deposited into the object. Now refraction is an example of a phenomenon called transmission, which is when a wave moves through a material. Now refraction is when a wave moves through a material but changes speed and direction when it transmits. So refraction is a type of transmission. So previously we've considered the process of reflection in waves. Reflection is where a wave hits a surface and bounces back. So in your ray diagrams for reflection you've got to draw a normal, which is a dashed line because it's an imaginary construction line. And when we're drawing our ray diagrams, we always draw the wave travelling in a straight line, we always draw the lines in with a sharp pencil, and we always draw imaginary or construction lines as dashed. So what we said is we had our incident or incoming ray, and we had our reflected ray, which is the outgoing ray, and we can measure the angles of these rays with respect to the normal. So we've got our angle of incidence and our angle of reflection, and what we know is that when an object carries out specular reflection, the angle of incidence equals the angle of reflection. But what is the process of refraction? Now refraction of a wave occurs when a wave travels into a new medium. So let's consider a wave traveling from air into glass. Now the light entering the new material is at the incident angle, it's the incident ray. So when a wave moves through a material we call this transmission. Now at this point when the wave encounters the new material, partial reflection can also happen at the same time as the transmission process. Now the light will hit a surface at the normal as shown on the diagram. Now the normal, as we said, is an imaginary line drawn to allow us to understand the process of refraction, so it allows us to measure out our angle of incidence. Now when a wave hits a new substance or medium, it changes speed. If the new medium is denser than the old medium, the wave will slow down. Now what will happen is this will make the wave change direction. So in this example, glass is denser than air, so it makes the wave slow down, and because it's hit the new medium at an angle, it will cause it to change direction. Now we call this change of direction of a wave refraction. So the transmitted wave has been refracted. Now this makes the wave travel closer to the normal than before. If it was speeding up, it would move away from the normal. Now we can measure how much the wave has changed direction by measuring the angle of refraction. Now in refraction, the speed of the wave is changed. Now this happens because the wavelength of the wave is altered, but the frequency of the wave doesn't change at any point. So if the speed was increasing, the wavelength would be increasing. If the speed was decreasing, the wavelength would decrease. But fundamentally, the frequency has to stay constant. Now as well as drawing a ray diagram, we can also draw wavefront diagrams. Now the wavefront represents the front of one wave travelling. Now in refraction, like we mentioned before, the speed of the wave is changed. So in this example, the light is slowing down. This means the wavefronts are getting closer together. We know this because if the wave speed is getting slower, the wavelength must be getting smaller because the frequency is constant, so the wavefront must be closer together. Now, if we consider this particular idea in our ray diagram, a common mistake is people mistakenly think the angle of refraction is the angle of the ray coming out of the material. That is not the case. That would in fact be the angle of incidence again. So just be careful. You always make sure to clearly measure the angle of refraction when looking at this refraction phenomena. Now, refraction of a wave can occur when a wave travels into a new medium. However, you only observe refraction when when light hits medium at an angle. You don't observe refraction when light travels parallel into the medium. Well, why is this? Well, to understand this idea of refraction and why it occurs, let us look at the model of refraction based on the marching of soldiers. As soldiers walk onto sand from grass, they'll slow down. Now, the important thing is if we imagine these soldiers marching onto the grass, because the troop are marching at an angle, some of the soldiers will hit the sand before the others in the same row, so they will slow down whilst the others in the row will keep on walking at a pace. So as a result, this causes this bending effect, so they'll move in a different direction. The same thing would happen with an unpowered car or truck rolling from tarmac onto sand. It would skid and change direction. In essence, the refraction process is the light skidding as it hits the new material. So just to clarify, the reason why refraction can occur can be shown on a wavefront diagram. As the wavefront hits the new material at an angle, some of the wavefront will hit the new material first and slow down, whilst the rest of the wavefront has not yet entered the new material and slowed down. So this means across the wavefront there's a difference in wave speed. This causes the wave to bend in refraction. Now, when a wave encounters a new material at a zero angle head on, the wave will change speed, but refraction will not occur. This is because all of the wave front changes speed at the same time as it encounters the new material at the same time. This means that whilst it will change speed, no bending of the ray will occur. So what have we learned so far? When a wave goes from one material to another, this is called transmission, and if it changes direction during this is called refraction. This is because waves travel at different speeds in different materials. Now, waves change speed as they change their wavelength, but their frequency will remain constant. But a wave will change direction and refract when moving between materials, when some of the wave changes speed before the rest of the wave. Now, to clarify, when a wave travels into a denser medium, the angle of refraction is smaller than the angle of incidence. We know this because the wave slows down and the wavelength has decreased. Whilst when a wave travels into a lighter medium, the angle of refraction is larger than the angle of incidence. This is because the wave speeds up, the wavelength has increased. Now, in the following required practical investigation, you're going to conclude this case by measuring the angle of incidence and the angle of refraction. So in this particular required practical, your aim is to find the relationship or link between the angle of refraction and the angle of incidence for a wave hitting a new medium. So to carry this out, we'll need a drawing grid, a rectangular glass block, a light ray box, a slit, a protractor and a ruler. So what we'll do is as follows. We would retrieve a power pack. We then set the power pack to 12 volts DC. We then place a rectangular block at the centre of a refraction drawing grid or piece of paper. You'd make sure the transparent side is facing upwards. You then use a sharp pencil to draw an outline of the block on the paper and ensure the block doesn't move when you're carrying this out. What you would then do is draw a normal as a dashed line. Remember, it's an imaginary line, so it has to be dashed, and draw the normal all the way through the block. At this point, at the normal, draw an array of instants 10 degrees from the normal, label it 10 degrees. Again, use a protractor to help you find the correct angle of instance, but you always take the angle from the normal line. So here, you've used your protractor and you've got your 10 degrees line. So you label this as clearly here. You then do the same for 10, 20, 30, 40, 50, 60, 70, 80 and even 90. Then you replace the block on the paper over its outline, ensure the block is placed exactly on its outline. You then connect a ray box to the power pack, ensuring the power pack is on the DC setting. You place a slit on the light ray box to ensure there's only one ray of light, so you've got one long thin line to show the wave. Now, the thinner the ray of light, the more accurate the result you will gain. You then use a light ray box to direct the light ray along the 10 degrees line so it enters the block at the normal, making sure the transparent side is facing upwards. You then mark the point where the light ray comes out of the box, and do this by placing crosses on the ray of light leaving the box, at least 3 crosses. You then remove the block and draw a straight line from the normal to the point where the light comes out of the block. Again, use a ruler to complete this task, and you can do this because the electromagnetic waves travel in straight lines. So at this point we then draw a straight line from the ray coming out of the block with the ray going into the block, as such, like that. And remember, the angle of refraction is between the normal and the refracted ray, as shown on the diagram. You would then use a protractor to measure the angle of refraction, and then what you can do is you can do this for all the incident rays: 10 degrees, 20, 30, 40, 50, 60, 70, 80, and always place arrows on your waves to indicate the direction in which the waves have travelled in this investigation. Now when you're doing this, my advice would be to carry this out with different colours, because it'll allow you to tell which line is which when you're measuring the angles, and provide an excellent source to revise from, as well as observing refraction. What you would then do is you would then fill in your results table with your observations. You then draw a graph of your experimental results, placing the angle of refraction on the y-axis and the angle of incidence on the x-axis, leading to a line of best fit being drawn, as shown on here. So what have we learnt in today's lesson? Waves can be reflected at the boundary between two different materials. Waves can be absorbed or transmitted at the boundary between two different materials. You should be able to construct ray diagrams to illustrate the reflection of a wave at a surface, but you should also be able to describe the effects of reflection, transmission and absorption of waves at material interfaces. Now, different substances can absorb, transmit, refract or reflect electromagnetic waves in ways that vary with wavelength. Some effects, for example refraction, are due to a difference in velocity of the waves in different substances. You should be able to construct ray diagrams to illustrate the refraction of a wave at the boundary between two different media, and you should also be able to use wave front diagrams to explain refraction in terms of change of speed that happens when a wave travels from one medium to a different medium. So if we've been successful and learnt in today's lesson, we should be able to detail the process of refraction, understand refractions due to the difference in velocity of the waves in different substances, and construct ray diagrams and wavefront diagrams to illustrate the refraction of a wave at the boundary between two different media. I hope you've enjoyed today's lesson, where we've looked at refraction in the waves topic for GCSE Separate Science Physics. Thank you very much for listening to today's lesson, and have a lovely day.